Kia ora koutou.
Welcome along.
Welcome along, everyone. So this is the NZVC webinar. We're here in the Becker offices in Christchurch. Thanks to Becker for hosting us. Tonight we've just got a webinar titled New Ideas for Modelling Energy Dissipation, Moving Beyond the Limitations of Rayleigh Damping. So our speaker for this evening is Dr. Rayleigh. So Rayleigh is an associate professor at the University of Canterbury with extensive expertise in the field of structural engineering. He earned his PhD from the University of California, Berkeley, and has since made significant contributions to the development of advanced computational tools for the nonlinear analysis of large-scale structures under seismic loading. So Rayleigh's recent work focuses on creating robust damping models that enhance the accuracy and efficiency of energy dissipation simulations in large-scale structures, addressing a critical need for high-performing computational methods. So with that, I'll pass across to Rayleigh. Yeah.
So, okay. Thank you, Jeff. I think I should speak to the microphone so that people online can pick up.
I think I'll pick up through these microphones.
Oh, this.
Yeah, just one final thing for those that are online. If you can just put any questions in through the Q&A rather than the chat function, we'll give an opportunity to have questions from the floor here for those that are live, and also questions, addressing any questions that come in through the Q&A online. So if there's any issues with the sound or any quality, please just jump on and note that, and we'll try and address them.
Thank you, Jeff. I think I'm not going to use the mic since that one can pick up my voice. I think I'm pretty loud enough. But if you find my voice too soft, don't hesitate to let me know. Thank you, Jeff, for introducing me. And thank you all for coming to this presentation. I'm very honored to be here. And thanks, Becca, for this place. Okay. Maybe before I talk about this, let me just give a brief introduction of myself as well. So Jeff already done some. So let me also say that even though I've been working on developing modeling tools, but I actually have some consulting experience. Before I came to Canterbury, I did some consulting in the US. And before I went to a PhD program at Berkeley, I also did some years of consulting work in Singapore. I've designed bridges, tunnels, underground structures, high-rise buildings. And when I was in the US, I worked a lot on the soil structure interactions of nuclear power plants. So that's my experience. So just to let you know that I'm not like a nerdy type, just know how to play math. So, so the topic is about modeling energy dissipations. So the context, so let me talk about the context of this title, right? So definitely, when we talk about modeling energy dissipation, the context is in the time history analysis. So when we try to conduct time history analysis to understand or to assess the capacity of the structures, and we need to think about how we can model dissipation in the structures. I think some of you might wonder, and why do we care to conduct time history analysis, which is very, very time consuming, and sometimes based on a lot of assumptions that cannot really be quantified. What happened? Is it because of the mouse? Maybe. No. Page down, page up. How about escape and see whether? Oh, okay, it's not responsive to keyboard. Oh, now we have it. I think now it should work. Yeah, I think so. I think so. Yeah, thank you. Thanks. This is the outlines, but don't worry so much about what I would.
Just talk a little bit loud.
Oh, okay. I'll try to talk louder. Don't worry so much about what I list here. These are things that I will talk about. But you will see on the left panel, you will see all the items that are listed there. They serve as a bookmark, also as a reminder about where I'm at when I talk about. Okay, so that's the background. So just now I mentioned about why we need to worry about time history analysis. I think the need to have a time history analysis, I think, could use this example, which is the Hotel Grand Chancellor, which was damaged during the Christchurch earthquake in 2011. And this building, after the earthquake, we noticed that clearly this building is tilted toward the east. All right. So what happened? You wonder.
Sorry.
Right, welcome. You wonder, right? So, and we also noticed the plane buckling in the RC shear wall. This is another classic example about how the wall might fail due to outplane buckling if it's not carefully designed. And to understand why this happened, so there's a schematic diagrams that set up. There was if we create a schematic diagram of the structured buildings, this is, notice that something is definitely said that this building is not a regular structure. It's not a regular buildings, right? I'm glad that Professor Okai is here because there was analysis done by him years ago using a time history analysis. And what do we notice? So here we have a plot of the envelope of displacement in both directions. When I subject the buildings to all different types of earthquake motions. And what do we see here? Obviously, we see that the building is ratcheting. Right? The building is actually ratcheting. It tends to vibrate towards the positive displacement directions rather than negative displacement directions. That we see more. Right? And in that Canterbury Earthquakes Royal Commission Report, Volume 2, this was documented there. And one of the statements that mentioned in that, which I can confirm, is that should we have used response spectra analysis, we might not be able to pick it up. Because in model response spectrum analysis, which is commonly used in the design for structures, typically assumes that the building will have an equal strength, equal stiffness, right? But notice the response of this building. Clearly it's not, right? It has a different capacity. Because this structure is actually non-symmetric, non-regular. So that says this ratcheting effects cannot be easily captured by using a model response spectrum analysis. That means a response history analysis is warranted, right? For evaluating the performance or capacity, of the building. So I hope with this example, I can give you sufficient reasons why we need to worry about time history analysis. I understand usually this is considered a time-consuming process in the design office. But there's another good example which Ethel has published in a recent paper in the bulletin of NZSEE. If you have dampers installed, again, model response spectrum analysis is not applicable as well, because the modes can no longer be uncoupled. So that justifies the need for response history analysis, or sometimes called time history analysis. And I'm going to show you some equations, but I promise to you that I only show 2 equations, and this is the first one. And these equations, I believe most of you have seen it before. This is the equations of motions. We have 3 terms there that resist You can treat them as inertial force, damping force, and the structure resisting force that derive usually based on material hysteresis. The right side is the equivalent forces due to earthquakes. So let's examine the first term, which is the inertial force. Inertial force, obviously, is a very intuitive term that basically says there's a mass, the mass accelerates, so they induce forces. That depends on mass, and we can always, well, quantify them rather easily through measurements, right? We can roughly give an estimate on what would be the weight or mass in the buildings, right? Of course, including all the non-structural components, we could have a good hand about it. The third term, that depends on the material properties. For nonlinear structures, we always see the stiffness changes with displacement. And usually it's well defined through lab measurements. We could measure the stress-strain relationship, or we can test something in the lab, right? We have a good hand of it. And based on FEM theory, the finite element methods theory, we could kind of set up a structural model for that. Okay, say if we can set up a stress-strain curve of steel material, concrete material, based on FEM theory, we know roughly how we can approximate the columns. Let's say using different approximation theory, whether detailed solid finite elements or some kind of the simplified concentrated positive hinge element or somewhere in between. It depends on the level of accuracy that you want to pursue. But definitely you have a good hand of it. You have a damper. Let me remind you again. We have damper. Damper actually belongs to this term. That's why you may notice that I said the third term is not a k times u, but rather it's a function of u, but could be a function of velocity as well. The viscous damper, we know how to quantify that behavior, so we should actually model it explicitly. In that sense, we are not trying to approximately using any model analysis. Right? We have a good understanding about that. And then we can allow to have modal coupling. So no problem with that. But how about the middle term, the damping force term? What is it for? How to quantify it? Well, that's blocking the title, but if you can help me kind of hide that if you possible. Don't worry about it if it's not possible. It's okay. Don't worry about it. Jeff, thanks. So the damping force PD, we usually use it to model so-called unmodeled energy dissipation. What is it called unmodeled? That means for those energy dissipation in steel, in concrete, in timber, or in any other quantified viscous damper, right? We could actually lump it into the PR term. But those that cannot be measured, quantified easily, we lump it into this PD term. And it's called unmodeled because this is a term that being used in some documents by ATC and peer. They use this, I think I kind of like it because it actually emphasizes that this is something that you have missed in your material models. So you're trying to capture something that you have missed. Okay. So what are these kind of energy dissipation mechanism? It could come from micro-cracking and micro-yielding in structural members. We know that concrete always crack. As you always see some micro-cracks happening here and there. Even for steel, you also see some micro-yielding because some inclusion, non-imperfection in steel material. Okay. So these are things that we cannot easily quantify them. And when we try to understand structures, we set out the models, and we can't afford to have exact nonlinear material stress strain curve everywhere in the buildings. That is just too much, right? Think about a building has lots of material points. You try to capture every single inelastic things, it's just too costly to do. So that means some of the components, we see that inelastic deformation is going to be very little. So might as well just treat them as elastic. That's a kind of common practice. Right? Some imperfect connections. In theory, in our minds, they are perfect. In our computer model, they are also perfect. But we know nothing is perfect. All the connections that we have, sometimes you will see some slip happening, right? When you load it, because of some insufficient turn of the nuts, it just could slip, okay? So this could induce some energy dissipation as well. And there's some interaction between structural components and non-structural components, okay? And probably one of the major one is the buildings never sits on a fixed base. It sits on ground, and ground could move. When any vibration happening from buildings, there will be some kind of radiation damping happening between the foundation structures and the surrounding soil. Those damping could be quite significant. But usually in our practice, we try to model structure as fixed base. In that sense, we can't miss that. And then if we miss that, we have to account it. How do we account it? Could be in this PD term. Of course, not ideal, but there could be something there. Okay. These are typical to be modeled explicitly using PR. That's why we use PD. Okay, and then you might ask, okay, so since we want to model PD, how do we model it? I think the most intuitive one is viscous damping, right? Why is it that we want to use viscous damping, which is equal to C matrix times velocity, U dot? Why is it that we like that? Because it's mathematically convenient. Well understood. Well understood, right? Particularly, when we learn about dynamics, we always start with a single degree of freedom system. Viscous damping is the one that we learn. So it fits well to the SDO of dynamics. And also in earthquake engineering practice, we talk about damping all the time. So that is the thing that we are familiar with. And it's easily understood in terms of damping ratio. For 1 degree of freedom and same thing for multi degrees of freedom. And we can talk about modal damping ratio. Okay? We talk about mode 1, mode 2, mode 3, mode 4 damping ratio. Right? That's an easy way to quantify energy dissipation. And we've probably seen this table before. This is a table that lists all the possible damping ratios understood during 80s and documented by Newmark in 80s. And talk about for different structures under different level of stress, what could be the damping assigned to different materials, right? Including some wood structures, some reinforced concrete structures. And recently, 30 years later, and people start getting more and more data, they also notice that, well, mode 1 damping sometimes depends on the building height. And the taller the buildings, probably the smaller the damping. I think it makes some sense because there are a lot of, like for example, the soil part, the radiation damping part could be less significant when the building is tall. Okay, now, so we understand that viscous damping is probably good enough, hopefully. And then now, as modeler, I guess, or as engineers, you might ask some questions. Okay, I try to think about what could be the question that we have in our mind. Right? The question for using the C matrix. Okay, that's my title of this slide. So first question is, should we use a C that's proportional or non-proportional? And should modes be coupled? Okay, that's my first question. I hope some of you also have this question. Second questions. How do we assign damping ratio for all the modes? Now we know some data that give us mode 1 damping ratio. But how about other modes? Do we assign the same damping ratio for all other modes or not? And how do we ensure damping forces are small enough? I guess since Rayleigh's book on dynamics talk about, well, hopefully they are small. Hopefully, right? So we hope that all the major energy dissipation has been captured by the third term. That's why this second term, we hope that is small, right? Hopefully. And if we have lots of degrees of freedom in structures, nowadays people like to model buildings with every single details, right? 3-dimensional. So the number of degrees of freedom could be tens of thousands. Nowadays, you can afford that, right? Or even millions, possible, right? So how can we ensure whatever C we use is fast enough to give me the solution? I can't sit there and wait for a year. I can afford to wait for 1 weekend, but not a year. And we know structures go into nonlinear range, the stiffness changes. Should we update C or not? If we don't update C, and think about this is the second equation that I'm going to show you, hopefully the last one. The damping ratio is equal to half of C divided by the square root of KT times M, where stiffness and mass. And that's my stiffness. If the stiffness drops to, let's say, 1% of the initial, what will be the damping ratio if I don't change my C? It will be 10 times. If you originally assume 5% damping, it ends up 50% damping. Is it what you want? And sometimes structures could go into a state of collapse. Maybe not collapse, but P delta, heavy P delta effect leads to negative stiffness. How can I ensure that I have positive damping during softening response? Right? And we know structures is never homogeneous. We have structures of different parts. Some could be made of concrete, some could be made of steel. Right? And probably very tall buildings, people like to use hybrid structures. So there are concrete buildings in the lower floors and steel structures in the higher floor. And how about foundation? Or how about some basements? They have a lot of soils containing it. Is it right to assume the same damping throughout? But what if I don't want? I just want to assign damping at different zones. And we know damping ratio, is it constant? Should it change? How can we assign amplitude-dependent damping or damage-dependent damping when the structures, some parts damage, right? Can I say, probably I need to have a higher damping ratio there? Can I do that? And how? And finally, I think this is the most important question from users' perspective. Can I get a C that I want? If I want to simulate the dynamic response of structure, can I assign a C that I want in terms of damping ratio? In particular, sometimes we say I want, don't really mean I want. The code wants it. Or some measured data requires that. How can I give a C that gives me that? Right? Could calibrate against measured data or calibrate against the code required data. So these questions are the questions that I have when I work on this. And let's see how, I hope that I can go through that slowly. Hope that question can stay with you a bit. So later in the following discussion is how I develop my model to address all these questions. I'm not saying that I could answer them fully, but at least try to address them. So before I address them using my model, let's look at what the current practice. The current practice is definitely the Rayleigh damping. Why? Convenient. You can find it everywhere in the software. And for so many decades of development, right? This is well understood, Rayleigh damping. This is very convenient, particularly for uncoupling modes, because we just assume that modes are uncoupled, easy, no worry about how modes couple. Another important factor, which is the C is sparse. Sparse means I don't have to store a lot of numbers. And when I compute for the solution, it's fast. Basically, it's a free answer. It's the same as computing the static response. It's just do it multiple times for different time steps. I don't change, I don't increase the cost. Right? So it's fast. Now let's see what's the consequence of this. So let me try to plot the damping ratio versus structural frequencies. And we know Rayleigh damping gives me two free variables to play. The two coefficients, one applied to the mass, the other one applied to the stiffness. Two coefficients. So that means I can talk about assigning damping ratio at two frequencies. So let's say I choose mode 1 and mode 3. Mode 1 gives me, I ensure constant damping for mode 1, mode 3. But you need to understand, Rayleigh damping actually gives you the curve like this. That means when you say mode 1 and mode 3 has this damping ratio, but look at the mode 2, will be smaller, hopefully slightly. But how about all the higher modes? They just keep increasing. And increasing to how much? We don't know. Usually people don't check it. I can tell you that if you're not careful enough, it could exceed 100%. I'm not kidding there. Let me see if I could. Here, I mean, for all the higher modes, is it possible? Very possible. Let's say if you want, I say, I'm going to update my C based on tangent stiffness, but I don't change my coefficients. I keep my coefficient the same. I just update it based on tangent stiffness, so-called tangent proportional C. This is one of the common terms that you probably hear people saying that. What happened? The damping ratio of all the new modes will just move along this curve. And you notice that, look at mode 1. It could actually increase. By how much? If you don't check it, it's very dangerous. Particularly, if you don't check it, it could go to infinity if you have zero frequencies. What happened to base isolated buildings? If you have base isolated buildings, you are imposing a very high damping there. If you are imposing very high damping, then you could become too optimistic about the performance of your base isolation. How about this then? This could also go to infinity, right? What happened to interstory drift, which is often sensitive to high frequencies? How about demands? Now you talk about demands on the non-structural components now. How people care about non-structural components, right? One of the big concerns in the Christchurch earthquake is that lots of damage in the non-structural components increase the downtime of the buildings. So this could become another concern. So this graph, which is done by Professor Edward Carr, published a paper in 2017 that shows if I were to use Rayleigh damping and try with different combination, and for one particular building, I try with measure with mode 1, mode 2, or mode 1, mode 10, make it fall to initial stiffness only or tangent stiffness only, and look at the residual drift all over the place, all different. Then which one should you choose? Which one is right? We don't know, unfortunately, right? And recently, I also look at this, but look at this, the interstory drift, and I look at the damping force at each floor. So let's look at this point. So don't worry about other curves, just look at the blue curve. Later, I'll come back to this again. Now, let's look at this one. This is the damping force exerted at each floor. Look at that floor. The damping force is 0.2 G. This is huge. Is it considered reasonable if you use Rayleigh model? There's a QR code that link to my paper. If you are interested, you can always take it and then link to my paper that published in Engineering Structures. So from now on, you will see me putting a lot of QR code, but I will not mention them. I just put it in the top and there's corner. Feel free to check out the papers that are published on this topic. Okay. Now we know there's some concern, some concern about Rayleigh. Okay, but should we, what is wrong with that curve, right? So clearly that's because of this blue curve here. right? Now, that actually forces you to always have that if you use Rayleigh. But you know from data, you measure, probably not like that. And the codes may ask you to design a building based on, let's say, 5% damping. But it's not going to tell you that it will be like that. Hopefully, they will say maybe 5% damping for all the modes, for example, right? And some study could show an increasing damping ratio in some of those recent studies, but some others will show a lower damping ratio in higher modes. I have a student working on testing steel buildings, scale down on the sheet table, measure data. Somehow the damping ratio of mode 2 is smaller than mode 1. So there's no good reason to say that damping ratio has to follow that kind of curve. I think when lack of information, I think a uniform distribution of damping ratio is probably reasonable. At least people could accept that until we have more information. And no reason to believe a high damping force for resisting rigid body modes. Think about base isolated buildings. Why should we believe that there's a huge damping force resisting it? There's no good reason to believe it. Right? We're not talking about strong viscous force coming from nearby fluid unless you're talking about offshore structures. Right? And no reason to believe a high damping force for degrees of freedom without mass inertia. This is on the high frequency end. In our models, usually we don't like to assign mass in every degrees of freedom. We always select some, usually at the floor, right? Because we think that this is probably good. And we are not relying on the density of the material. We're relying on a lot of added weight on the structures. So I think a good model should be able to give you this uniform damping. And hopefully it could tie down to 0 at 0 frequency, rigid body modes, or at high frequencies, right? Hopefully it doesn't give you huge damping force and pollute your result for interstory drift. This one is not good. Okay. Are there any other options? Let's say Rayleigh is not good, right? We know Rayleigh is not good. Any other options? There are two classical options. One is called Corky damping. The other is called Wilson-Penzen modal damping. I think it's kind of commonly known as modal damping, but I kind of want to give a credit to Wilson and Penzen. That's why I always call them Wilson-Penzen modal damping. But you know they are the same thing. So the questions, I think, for these two models is that they all require computation of structural frequencies and mode shape, particularly structural frequencies. Computing them is not cheap computationally. If you have very small structures, yeah. But you have very large scale structures, no. If you compute it for once before the analysis, okay. But if you do it for at every single time step, no way. No one would want to do it. So you can't update C basically using this option. Second, as I said, C cannot be easily updated when KT changes, when tangent stiffness changes, right? Because of no time. So a large increase in delta if you don't update. So that's the consequence that you have to face. Corky is even worse. It's not going to give you very good uniform damping. Some, if you are not careful enough, it could give you negative damping. That's clearly not what you want. You want the energy to be dissipated, not gaining energy. Right? Wilson-Penzen modal damping, you may select the first few modes. Okay? If no one can afford to compute for all the modes, maybe first few modes. Could be up to certain numbers. But then you need a beta K, another tangent stiffness term, to avoid undamped higher modes. Later I will show you when there's undamped higher modes, what will happen. So they both result in a fully populated C. So the computations is going to be huge. Of course, I know, since I know it's here. We do have some iterative procedures to do that, to avoid using C explicitly. But I want to say, convergence is not guaranteed. although some study demonstrated convergence with a few iterations. Okay, so these are the current practice, which I think are not good. Definitely not Cauchy model damping. Maybe I know people start using that, but I do think that if you don't update it, you are going to end up with a high damping. If you update it, sorry, you can't. It's just too expensive to do so. So I think about an idea. So remember that curve that I showed you, that Rayleigh curve, terrible. Clearly, obviously, the easy way to fix it is to flip the curve. So to flip it, I basically take that Rayleigh curve and flip it upside down. Then I can get zero frequencies. Zero damping at zero frequencies and zero damping for infinite frequencies. And in between, I get a very nice bell shape, but on a log scale, not on a linear scale, on a log scale. Nice, right? This is a nice curve, very smooth. Positive throughout, easy to control. We can control the location of the peak. We can scale the value of the peak, right? Up and down. Now, this gives me a good bell-shaped damping ratio versus frequency. Obviously, you say, well, I want a uniform one. Well, you can add more. If you have two bell shapes, you can sum them up, you get this curve. Three bell shape, you get this curve. Let's say this is data that I have. I somehow get a uniform damping for these 6 frequencies. I can fit 2 bell shapes or 3 bell shapes to give you that. Compared to what Rayleigh and Cauchy can give you, definitely the green one, which is this proposed bell-shaped curve, can do a better job. Much smoother and always positive damping. Smooth, right? No oscillation, no funny oscillation. Maybe a bit of oscillation in that so-called uniform, but it's within tolerance, so that's not too bad. So then talk about computational efficiency. So granted, the C matrix using this bell shape will still be fully populated. But we don't have to implement it as a fully populated C. We can somehow find a way to expand it, to make it like this, completely sparse. And look at the comparison of numbers. Now we have significant reduction, at least half of this. But this only have 200 degrees of freedom. If I keep increasing the number of degrees of freedom while keeping the same number of bell shapes I have, this one plot the number of non-zeros of the expanded version of C versus the fully populated C. You can see how it decreased with the number of degrees of freedom. Okay, and the blue curve shows the comparison of number of non-zeros, and the orange curve shows the time ratio. So how much time is saved? Look at this one. You have 10,000 degrees of freedom, which is not considered big now these days. And the ratio, number of non-zero is 1%. Same thing for computing the solution time as well, 1%. So it's a very good news. In fact, you keep going, where n is the number of degrees of freedom, the larger the number of n degrees of freedom, the better it is. Yeah. And now, actually, I'm also continuing to work and improve this, which I will not talk again, but I make it even better these days. That could run even faster and without worrying about sparse matrix storage. Okay, let's do an example. Right? Enough said. Let's look at an example. Okay. So here we have a 10 stories buildings, steel buildings, with a yield strength of 250 megapascal. And I try to consider 3 options for damping: Rayleigh, Wilson-Penzer model damping, and the bell-shaped model. And I select the first 6 modes to ensure to have about 5% damping. The first 6 modes give me, I think, 90% of the participation mass. So I choose this 6. And let's say I choose to match only 2 modes, first 2 modes for Rayleigh. And then for Penzian model damping, I match these 6 modes, and all other modes are just undamped. Okay. And then I have this my damp. Okay. And when I work on that time, I say, well, let's say C is not updated. I make it constant. So it's called initial stiffness proportional. So C is constant throughout the whole time. It doesn't matter whether the structure has yielded or not. I subject this to these ground motions. The PGA is about 1G. And then this plot shows the result of the roof drift for the top graph and the base shear for the bottom graph. The top graph has 3 curves coming from Rayleigh, Wilson-Penzian model, and the proposed bell-shaped model. You'll see that the displacement looks okay. They are kind of similar. There may be only some deviation in Rayleigh's one. I think the reason why we have a small deviation is because of they all have the same lower mode damping ratios. And I keep C constant. Later, I have more examples, which I will show you the deviation in drift could be significant, and which Edoka has also shown that before, but not in this example. But I want to highlight the base shear part. Now, the Wilson-Penzian model damping give undamped higher modes. So you would see zigzagging in the response. Okay? This comes from the higher modes. That's why that shows you the importance of damping them out. You might wonder, well, they may be not a big deal. Right? It looks small. It's okay, we're happy with it. But this, because of the global response, let's look at the local response. Before I go to local response, let me remind you, the maximum base shear is about 0.25 G. Remember this number? Later, I'm going to show you some strange thing compared to this number. So this plot, which I'm showing before, right? Plot the story shear and the damping forces exert on different floor. Okay. And obviously, you look at the left graph where it shows the story shear. Now, obviously, Wilson-Penzian will give you a higher story shear. Right? It's because of undamped higher modes. Those undamped higher modes give you larger one. They may be small at the lower floors, but the difference is significant on the higher floors. And later I can show another example. Actually, significant difference could be on the lower floors. And remember, I also remember that number, 0.25 G for the maximum base shear. Look at this one, 0.2 G. You see the damping force? The floor damping force is 0.2 G. 80% of the maximum base shear. This is no kidding. This is a huge number. And use the bell-shaped model, it doesn't give you that. Even if I make the C unchanged. I have a higher damping ratio, but I don't have this kind of strange things going on. Okay. I say, okay, life is not that easy. I don't always get uniform damping. I get some measure data. What do? Okay. Let's say you say you can do uniform damping, but how about other types? Well, I could also do a linear if you want. Doesn't matter, however you want. It be linear this way or linear the other way. Or you can do trilinear. So you provide some kind of caps. Or the other way. It's up to you. So I show the flexibility of the bell shape to give you all kind of curves you like. And not only I say I have 2 parameters to control the location of the peak, I can also control the width of the bell shape. I can make it narrower, or I can make it wider with some additional parameter to control them. Or I don't have to keep them symmetric. I could control such that I have a larger drop on the right side or on the left side. So let's say you want, I like this damping ratio. I say at 1 Hertz, I have the transition. Below 1 Hertz, 2%. Above 1 Hertz, 5%. I just want to do this. I don't know how to do a transition. Is it possible? Well, if you use the initial bell shape, it can give you this. Probably don't like it. But remember, I showed some control that I could do. I can make this transition sharper and sharper. Now I can have an idealized step function. Of course, then you ask, what's the consequence? Well, you have to have a longer computational time for this. That's the downside. But it's really up to you, right? So no free lunch. Whatever additional flexibility that you like, you have to pay more. Okay. But you say, okay, remember I said structure could go into collapse state. It could experience negative stiffness. Then would I have positive damping? Okay, let's look at the Rayleigh case. And in recent discussion, a lot of people suggest, forget about the mass term. They say mass term is not real because it kind of suggests that some kind of the air friction, the mass must be removed. Fine. So let's say we have tangent stiffness proportional damping. Right? Let's look at 1 degree of freedom. Keep it easy. And a force displacement, whatever you have, could be base shear versus roof drift. And initially, positive stiffness. Beyond that, definitely have a lower stiffness. Okay, it's still hardening. So let's draw the damping ratio versus frequency. But now we need to extend it to include negative stiffness. So I plot this curve. On the right side of that vertical axis is for positive stiffness. The left side is for negative stiffness. Okay, and the damping ratios is computed based on this. Well, you can just beta KT and then divided by the frequencies. Then you can get this curve. Okay, and because of the negative stiffness, the sign of stiffness need to be associated with the frequency as well. So I have positive frequency and then negative frequencies. Okay, so let's say initially omega 0, this is the damping ratio I have. Now, when yielding happens, I drop in frequencies. We have now a smaller stiffness. So my damping ratio drops, but still positive. So I'm happy. Yeah, maybe not at the level that I want, but at least still positive. Makes sense. But what if you have a negative stiffness? Well, then you move to here. You move to here, as I said, when the damping C follows stiffness, you move on this curve. Now you move to the other side, and you end up with a negative damping. Now this is concerning. This is concerning. You are gaining energy now. You're not losing energy. Is it what you want? Probably not, right? So even with Rayleigh damping has additional term, mass term. It just delay this a bit, but you could still see negative damping. So Rayleigh damping proportional to tangent stiffness will likely, maybe I shouldn't say well, may result in negative damping for softening structures. Okay. So the bell shape that I have can be extended to negative stiffness region. So this one, I have 2 graphs. On the right graph, you see the damping ratio versus frequency associated to positive stiffness. I can also control the one on the associated with the negative stiffness. That's where you see negative frequencies. Now I can control that to have the same damping ratio. Let's say 5% here. And don't worry about type 2 and type 4, it's just different types. If you're interested, there's a QR code, you can check out the paper. I don't have to force myself to have the same damping, I can adjust them. I can have a higher damping or lower damping when the structure is experiencing softening ratios. Okay, fine. You say that's cool to have, but is it really matter? Does it really matter? So I'm going to show you something. So this is another numerical example that I've done. And now I have, I'm sorry, I've used these imperial units. So the U strength is 50 KSI. And the columns has an 8% softening ratio. So it's not really significant, 8% only. Yeah? But because of P delta, this kind of thing could actually complicate the problem a bit. Now this one plot the damping ratios versus frequencies. Now I'm using a very strange scale. It's not called log scale. It's called symmetric log scale. It's a symmetric log scale so that you can, when you plot log scale, you cannot plot negative number. Right? Negative number doesn't exist in log scale. But in a symmetric log scale, you kind of play a bit of trick. The trick allows you to kind of squeeze and scale things a bit for positive number and then for negative number as well. So I'm plotting damping ratio versus the frequencies, which include negative number. And remember, this is a log scale, so the blue one shows the bell-shaped damping ratios, but the red one shows the one coming from the stiffness proportion. So for simplicity, I just ignore the mass term for now. Okay, I just keep this one. It looks like a bit odd. It's like a linear line because this is a log scale. So that's for positive, that's for negative. And then I ensure my C is proportional to the tangent stiffness proportion. Okay, so that means the damping ratio is going to move on the curve. So subject it to the out central north-south components. And look at the result. This plot the roof drift. The blue one is based on the K proportional, Rayleigh without mass. And the red one shows the using the bell shape. Obviously, now you can see, look at the drift, residual drift. It's indeed significant. Maybe in the first example it's not, but this example shows it could be quite significantly different. And you might wonder, why did the Rayleigh give lower drift? Because remember, you back to that curve again. The damping ratios using the K proportional is much higher, right? And those green circles are the initial elastic frequencies. Right? I shouldn't say Rayleigh, I should say K proportional, but yeah, if you remove mass term. And let's plot the base shear versus roof drift. Okay, then you see this hysteresis. Indeed, you notice the softening behavior, right? And look at these energy dissipations, cumulative energy dissipation throughout the whole duration of loading. Obviously, increase. And the blue one, again, I use a consistent color. So the blue one is for the K proportional, the red one is from the bell shape. Obviously, because you have higher damping ratios for the higher modes, that's why the K proportional dissipate more energy. But the bell shape, because I make it constant, so it dissipates less. Then you ask, okay, fine. So what's next? Let's examine this softening behavior. I put some markers there to highlight these are the softening response. When softening response, let's look at the EDT. Well, that's a little part. Obviously, it's not easy to see the difference. And particularly during the softening response, we're not looking at the cumulative number, we're looking at incremental energy dissipation. So we should look at the derivative of that. So ED dot time derivative. So let's plot the time derivative one for that particular short time frame. And this one indeed shows that the K proportional gives you negative damping. It gains energy instead of losing energy. This one gives me positive damping. But you may say, well, it looks so small. But let me remind you, ED is not an energy dissipation only from one mode. It's for all the modes. Remember, K proportional have very high damping ratio for all the higher modes. So they have very high contributions. This one, negative, is a net. It's a net effect coming from all the modes. So all the higher modes have very positive damping, but the first mode has negative damping. So even though the net is small, it actually implies that, look, the first mode actually has very high negative damping. Okay. Now then, okay, so that's how I address that. The next question I have is that, Well, the structure is never homogeneous, right? I have concrete structures, steel structures, timber structure mixed together. Can they have different damping? Look at this classic diagram that we often see in the books on dynamics. You say 5% for the superstructure, 10% for the foundation or basement, all because of surrounding soil. Well, classical models are designed for global damping. They are not for this type. And people say, oh yeah, let's form the seas separately and then assemble them. You will see that in a lot of textbooks saying that. And I would say it will not work, unfortunately. Based on my experience, it will not work. It may work if you use Rayleigh, but only when you use Rayleigh. But Rayleigh is not uniform then. So when you say 5%, what do you mean by 5%? 5% for which mode? So they are not necessarily work. And of course, this idea also gives rise, I guess, the elemental damping share the same idea. Can I form elemental damping in different parts and then assemble it like that? Well, I've done some study and I use that idea and ensure my global damping is 5% for the first several modes. But look at all the higher modes. I have to use log scale for the vertical axis. The damping there is way higher than 100%. Is it reasonable? I don't know. If this is your intention, so be it. But I guess I doubt this is your intention. You probably don't want to see thousands or tens of thousands of damping, right? Values on the higher modes. And not only that, even though you say 5% for the superstructure, 10% for the foundation or basement, you hope that the global will exhibit maybe 7.5%, somewhere in between. But I can tell you, no. The global damping will be smaller than 5%. Will be smaller than the minimum of the two, unfortunately. Unless you use Rayleigh. Rayleigh could be quite different. But if you do model damping, no, it will not. The global damping could be much smaller than 5%. And the global damping for the higher modes is much more than 100%. And in order to achieve 5% for the lower modes, the elemental damping could be way more than 100%. Now the question is, what exactly do you mean by elemental damping ratio? What does it mean? How could you have more than 100%? We never see that, right? We extract any components, shake it. Do you see that it critically damped? Probably not, right? Another downside is, okay, I can do this. Let's say I accept that. But the structure is going to suffer change of stiffness. Do I keep my C the same? If I don't, I want to change it. How do I change it? If I change it, you have to redo all your calibration. From time step to time step? Probably not. And the modal cupping effects is going to be huge. Not just the damping on the higher modes. In between modes, the cupping could be huge. Yes, many of you could believe that modal cupping is real. Yeah, maybe. But my question is it what you want? If this is what you want, go ahead. But hopefully you know this is what you want. If this is not what you want, then I don't know. You need to be careful about it. So I said, no, I don't agree with this. My suggestion is use the Belgian model with a consistent assembly method. Then you can ensure that. But I'm not going to show you the math. Welcome to check out my paper then. And Edo was part of all this as well. So let's use an example to illustrate that. So here we have 8-story buildings. I'm going to say 5% for the floors. Okay, a lot of mass there probably makes sense. For the column, I'm going to play with different things, 5% and 1%. So what happened? If you use the bell shape with a consistent assembly method, if you have 5% everywhere, the global damping also 5% everywhere for all the modes. Definitely consistent. Right? You assign 5% to all the elements, you hope their global structure also exhibit 5%. Okay, and I can ensure that. If I have 1% for the columns, then I have weighted average. Right? Weighted average. That makes sense, right? 1 and 5 average is 3. Hopefully, based on the number of elements or columns, number of beams, clearly equal numbers roughly between columns and beams. So you probably think that if I have more columns, probably it will be less, more beams, less columns, there will be less, more, right? Towards 5%. Now let's subject this to this ground motion again. And here, the top show the roof displacement, the bottom show the base shear. The blue one shows all elements 5%, and the red one shows the column only had 1%. And now, because the weighted, remember the global actually shows 3%, so now you have a larger drift. It's a larger base shear. Expected, right? At least intuitively, you believe it. And look at intertoroidal drift, right? Indeed, I have a, because of I have a smaller damping force, now I have a larger drift, right? For the red curve. And look at the floor damping force as well. Obviously, I have a smaller damping force. Right? It makes sense. At least, I'm not saying it's accurate. What I'm saying is reasonable. Finally, okay, let's say I'm happy with that. But how about damping is not constant? I can change it, right? You're damaged. My student that's there says damping could be amplitude dependent. Right? How do we handle that? Okay. We say when a building is damaged, its stiffness K changes. And the diameter C also changes accordingly. Well, in particular, I guess in your mind, probably you don't know what C means. Right? You can't measure C. So we actually in your mind is damping ratio. How could damping ratio change with damage state? Or in particular, can we say damping ratio is a function of position, of displacement, of strain, of stress, plastic strain, frac strain, damage, or whatever parameter you like to quantify the state of the material, beams, columns, components, substructure, right? Can I do that? Let's say for nonlinear material, okay, it goes through this hysteresis. I only draw the first quadrant, right? As the stiffness changes, can I assign different damping ratio at different paths? Well, if we want this, okay, it doesn't have to be stress strain. It could be force displacement. Some components, phenomenological elements type, would be plastic hinge elements, more simpler rather than stress strain. No one can afford the fiber section modeling. And let's say this we can do, and can a change in material damping be reflected on the global damping? Can we do that, right? If it is, and can be simulated numerically, is what I hope so, it can give a better calibration power for simulating inelastic structural response. Okay? I'm not emphasizing accuracy, I'm emphasizing that it gives you the power for calibration. Now here, I have two undergraduate students work with me. These are shake table tests. Well, actually not shake table tests, just an impulse free vibration test of some multi-story simple model frame in the model structures lab at UC. So they take up the two-story model frame, and then they try to introduce some kind of impulse load, and then let it free to vibrate, and then measure the damping ratio from segment to segment. And then notice the damping ratio does change with the drift amplitude. Okay? The amplitude start from 3%, then dissipate all the way to 0. And they also notice the damping ratio also drops. Of course, you say, well, this structure is tall. Granted. But I guess in real buildings, probably similar. Right? Well, I don't know. But at least this one exhibits that phenomenon. The real structure probably exhibit. Now raise the question that damping ratio is not constant. Now I play with this idea. I use the model by Professor John Hall in 2006, 10-story shear type buildings. So there are only 10 degrees of freedom. It's a shear type. And then in each column, there are different stiffness from story to story, but they always have the same yield displacement, I think about 1.1 cm. And then when it yields, the hardening ratio is always 3% of the initial stiffness. So 3% hardening. And then I consider three options to model this. First one, I use a Rayleigh, make it initial stiffness proportion. Second one, I use a Rayleigh, but then I make it proportional to tangent stiffness. The third one, I use the bell-shaped model. But the bell-shaped model, I have three sub-options. The first option is that I say, I don't care what the stiffness of the columns, I'm going to assign 5% throughout. So during the initial elastic stage, 5%, plastic state, also 5%. And second sub-option, I say, initially 5%, but plastic state is 20%. You might wonder why 20% is a huge number. Because the model that I developed allows you to assign damping ratio to mass and stiffness separately. So since I only assign to the stiffness, I don't assign to mass, the mass damping is constant. So the effect of this 20% will not show as 20%. It actually will show at 10%, because part of it goes to the mass, and mass doesn't change. It's damping. The third sub-option is that I make it 45%, make it even more drastic. Okay? This will actually lead to 15% in the global damping, but later I will make it clear. Again, I subject this to this ground motions. And let me explain a little bit before we analyze the result. Let's show what it really means by how the damping ratio actually changed. So I plot the Rayleigh curve here, but remember I use a log scale, so it looked like a curve like this, an upward concave curve. So this is matched based on the recommendation by Professor John Hall. So the first mode is about 5%, but the second mode is not really 5%, but slightly higher. But all other modes were just very high, go up to 20%. If I say, let's say, if I have a case where all the column yields, all the columns, right, from story to story, what would be my damping ratio? So obviously the frequency would drop and the damping ratio will increase. Look at mode 1. And do not think that this is unusual, because seems like quite unusual, but some of this mode was designed that it could happen. It should happen. Later I'll show you that. Now the first mode become like nearly 20%. That's for option 2, tangent stiffness proportional. Then you ask, how about option 1? Option 1 would basically, you have 3% damp stiffness. That means if you do the calculations, right, the damping ratio, all of them would just increase by 5.8 times. So the 5% would become 30%, roughly. Okay. But the higher one would become even higher. Here, look at using bell-shaped one. Now, I use the green bar to indicate this a range of elastic frequencies. I'm not going to label them again. You remember it. The green lines for the elastic frequency range, and the red line with open circle is for the plastic frequency range. So the elastic frequency range using the model option, right, initially all 5%. If you use 3A, always 5% throughout. So when all the column yields 5%. Okay, let's run the analysis and then try to examine the damping ratio history. So from time step to time step, I extract the C and then compute the modal damping ratio based on that C. Right? Get a diagonal. Right? You convert to the modal space and extract all the diagonals and then compute it. What would be the damping ratio experienced by the system? So option 1, remember I said, look at the case when there's a range of positive frequencies, and it did happen. Or there's a time when all column yields. And then the damping ratio that experienced by the structures could be way more than 100% in the higher modes. Because you don't update your C. It's an initial stiffness proportional. Option 2, now just oscillate on that bow, right? That curve. About mine, using bell shape, 3A, 3B, 3C. The 3A show 5% throughout. 3B, now, when yielding happens, now you will see some higher damping ratio. It gives you 10%. And then it could give 15% even higher case 3C when you assign 45% to the column damping ratio. Now look at the result, global sense. Now that you know the history, now let's see how they actually being shown in the global response, how they affect the global response. So the first one shows the roof drift. The second one shows the base shear. Normalize the yield base shear. So that's why whenever number exceeds 1, you see yielding. And then look at the total damping force collected at the base. So it's like you sum all the damping force at each floor compared at the base, right? So basically this is resisting the base shear. So if you use Rayleigh with initial stiffness, look at the number, 0.5 or 0.6 VBY. 60%, the damping force could resist up to 60% of the yield base shear. This is huge. Do you believe it? I don't know whether I can believe it, right? And obviously, where did they happen? They happen when yielding happens. Whenever yielding happens, obviously, Rayleigh will give you very high damping. But you say, okay, granted, I'm going to try with the Rayleigh KT. I mean, tangent stiffness proportional. Now, good. You definitely reduce the damping force from 0.6 down to about 0.2 or 0.25, right? And then look at the drift. Now you end up with different drift, right? Obviously. And if you use mine, I can reduce it even further because I have even lower damping, right? 5% drop, so we can have it even lower. Only 0.1 on the plus side. The negative side, yeah, about 0.1. Okay, and that seems in the spirit of Professor Rayleigh, damping force is small enough. Hopefully, right? They are small enough. And you control them to be small. But if you think that they are not small, I say, I want it larger. I make it, as I said, you try with assign higher damping to the plastic state. Now you can have a higher damping force and reduce the drift a bit. Or even higher. Well, it's up to you. So this gives you some freedom to control the damping force you exert on the system, and then the drift will be different. Not only global one, let's look at local one. So this, the left plot the interstory drift ratio, normalized by the yield drift ratio, and the right one plot the floor damping force. Look at this one. Is it what you want? 0.2 to 0.25 G? Do you believe it? I probably don't. But I say I'm going to use Rayleigh with tangent stiffness proportional. Now I get a larger drift, right? Larger interstory drift. Now you can see there's a huge difference at the base. But also the damping force, they still remain like 0.2, 0.25 G. So even though you kind of relax and have a high interstory drift, but look at the damping force there, it could still be high. And is that what you believe? I don't know. But I probably don't. So I want to control it. So if I use a bell shape, now I can reduce it. The damping force now reduced to about 0.1 G. And because I use 5% damping, 0.1 G, now I still have a similar interstory drift, okay, at the base compared to the Rayleigh tension case, right? So I can control the drift a bit, but at least my damping force is not strange. Of course, you think that, well, maybe the drift should be smaller. I add a bit more damping. Yeah, I can have a smaller drift or even smaller. But the damping force, the maximum floor damping force is controlled at 0.1 G. Right? Okay, what's my take-home message? Thanks for waiting until now. You might wonder, what's my tail message? I think Rayleigh damping C, whether proportional to initial or tangent, they result in unreasonably high damping forces. It doesn't matter whether you use tangent proportional. People have been talking about using tangent proportional, think that they could reduce. Some say that even reduce too much. Right? I think Professor John Ho will say it's too much. But I think no, actually still result in unreasonably high damping force. And I don't think it's suitable for structures with softening response because it would induce negative damping. If you don't check it. Huh? And definitely not suitable for hybrid structure with inhomogeneous damping. Definitely. And if you consider existing classical damping models like Cauchy or modal damping, well, I don't think they are better. They are actually could be computationally unfeasible, particularly Cauchy. Yeah. Some say I just use the iterative procedure, but I think it does not solve all the problems. Yes, it probably solves one in the time, but you still cannot control it in terms of how you update it. The recently proposed Belgian damping model that I've been working on allows you to have any user-defined damping ratio for all modes. Up to you how you want to control it. Definitely no spurious damping forces, no strange large damping force. Definitely ensure positive damping during softening response. You don't gain energy, always dissipate energy. And suitable for hybrid structures with inhomogeneous elemental damping. You can now talk about 5% for superstructure, 10% for basement structures. And will give you good results. And my dream is beyond that. I can even control such a damping ratio can be calibrated against measured data. And can be a function of damage state. Can be amplitude dependent, damage dependent. That's my dream. Okay, I need to acknowledge who will help me. Of course, Mr. Edoka. He inspired me on this. We have a lot of discussion about the problem of damping. I learned a lot from him. And the other, Lei Chang, my former PhD students, we have some discussion about how to implement it. And then finally, also thank to those who try the bell-shaped model. Some of them have given feedback. Some don't know, never talked to me. I don't know why. I think Marie has used that, right? Yeah. How was your experience? Don't worry. Clearly, you have nothing good to say. No, I'm kidding. So I think that definitely it has potential. For my view, it has the potentials. Granted, the computational time may not be as fast as you hope to see, but I'm working on a new procedure that could make it even faster, which I will discuss it soon. Okay, that's all. Thank you.
We might start. There's 4 questions online, so we might start to have a look at those. So Greg's got some good questions. So question 1, if we want constant modal damping over a range of periods, what is the advantage of using many bell-shaped damping curves compared with one much wider damping curve with a flat top? And hopefully he did not misunderstand the damping curve width discussion. So do you have any comment on that?
I don't quite understand the question. Was it, I'm not using many bell shape.
So I think it was when you're doing the fits, like whether it was one curve, whether you was going to multiple.
Oh, you mean multiple kind of this?
Yeah.
I mean, the oscillation of it. The oscillation can be controlled such that within your tolerance. That means you can give a near constant. Much wider damping. I see. So if you allow to have a bit of error, plus or minus, let's say 0.01, for example, then with a fewer bell shape, will be faster in terms of computations. So that's the advantage of that.
But there'd be more variation in damping for different modes.
True.
Is it?
True, but then if the variation is like say whether 5.05% to 4.95%, I guess that is probably considered acceptable.
So the next question from Greg was, I think Tim Sullivan did some work on tangent stiffness proportional structures. I think that he indicated the effect of this negative damping was insignificant. Your results indicate that it can be very significant. Is Greg missing something? Do you have a comment on that?
Well, I don't know the comments by Tim in his work. I know that they work on it, but when you say insignificant, it could depends on different structures.
But you have seen results where the negative damping is quite significant.
Yeah, I think that if they say insignificant, which I don't know, then but I think they work on it to actually say that they want to remove those stiffness associated damping with negative stiffness, right? So they remove that. If there is significant, they could have kept that. I don't know about that work well enough to say, but I do think, granted, sometimes when you show a case, you would probably want to design a structure to demonstrate that. So I can tell that when I design that structure to demonstrate that softening behavior, there have been some fine-tuning in order to demonstrate that effects. In the real structures, I don't know. I think that if a structure is going to the collapse state, that's a significant softening, I do think that it would become significant. I think it would become significant.
So we might
good question.
Jump forward. We can always go back to Greg's subsequent questions there, but why the damping force could be significantly different, but the total base shear is similar using different damping models. Total base shear is a critical element for structural design. So if the base shear is the same, then the design demand will be the same.
I see.
So
I believe that that could be related to the last example, right? So the base shear is pretty much dominated by lower modes. That's one. So if you control lower modes right, the difference between different models probably not too bad. This one view. Second, because the hardening ratio is small, let's say I choose 3% hardening. So usually the difference, think about that 3% off. That's why you will not see significant difference in terms of forces, base shear forces. But in terms of displacement, then it could be significant. Because think about the curve is like that. It's a pretty much pretty gentle slope. So you have to off by a lot of displacement in order to see a large difference in terms of forces. I think that could be a potential reason for that.
I think also potentially that in a response, the inertial forces and the column forces probably dominate, right? So while your damping forces might only be 5% of the total contribution, they can be quite different without the total base shear being wildly different.
Yeah. So if I do it right, so in the Belgian model that does it right, you can do to make it small, to make it insignificant in that sense. That's why the Rayleigh one doesn't do that, right? If they could induce very high damping force. Yeah.
So the follow-up question to that was how to implement this new damping model into commercial software such as ETABS or SAT.
Good question. So I have that implemented in OpenSeas. I wanted to set it in normal code, which I've been talking to him. So in the new algorithm that I'm working on, should be easy for you to implement. I would share the paper that I recently published in a conference. And
I can make some comments by question. Several points that come to mind. We talked that the damping forces are small. If you have an elastic 1 degree of freedom structure with 5% damping, the damping forces are of the order of 10% of the forces on your structure. So, 10% is about, for a 5% damp structure, you're looking at that sort of order. What we found in 1978, and the example was Rob Jury's master's thesis, that with Rayleigh damping, we had damping moments at the joint which were greater than the yield moments of the members framing into the joint, 1,000 kilonewton meters. The is that's the stage, and ever since then, we've always computed the damping actions every time step, so we actually know what's going on, which something that's a real mystery is why other software doesn't do that. Because if they talk about equilibrium, if you don't know what the damping actions, you have no idea what equilibrium you've got either. So that's one aspect that's important. You talk about the tangent stiffness. Examples going back to the 1980s. Yes, the tangent stiffness damping will give you larger deflections because you actually have lower damping actions. But it depends on whether you're using a tangent damping model to compute your damping actions or whether you're using a secant damping model to compute your damping actions. That becomes important. If it's a strictly tangent model, then you've got real problems for a nonlinear structure, because when you have, if the structure has hysteresis, then your damping has hysteresis. And so you end up at the end of the earthquake, all motion stopped, and lo and behold, you have still large damping forces, which is quite surprising. So that's one reason why we've built in several options if you want to use Rayleigh damping. Rayleigh damping has been around since 1894. Rayleigh used viscous damping as a mathematical convenience. He was actually playing with musical strings. So it wasn't buildings, it was musical strings. It has no physical or mathematical justification. It's, as you showed, the damping ratios are anything but what you want. In Rob Jury's frame, the highest modes had about 3,000% of critical damping. And the point is that you say that the higher modes are excited by the localized deformations. All deformations can be represented by a combination of mode shapes. If you've got large local joint rotations, because the beams will let go, then you've got to bring in the very, very high modes to get that localized joint rotation, and they have several thousand% damping. You get big damping actions. You can't do anything about it. And in terms of other aspects, you talk about modal damping ratios. I think when you have non-proportional damping, you have to forget about damping ratios. Because if you have non-proportional damping, the frequencies are complex numbers and the damping ratios are complex numbers. You use multiplication of the diagonal terms only. I think that's totally wrong. You have a matrix with off-diagonal terms. You've got to consider those as part of.
This one I have to a bit disagree with you.
Okay.
Because that depends on how you how you account for the off-diagonal terms.
Yes, well, they're there.
Yeah. So if they are not significant, so actually in the latest paper that you involved, so I have coupling in the modes, and then I excite them, and then I try to compute the damping ratios based on logarithmic decrement.
Yeah. And
then compare against with the damping ratio based on the diagonal entry only. And then they are consistent.
Okay, but the off-diagonal terms actually can be quite significant.
Yeah, if they are significant, then they become an issue. If they're insignificant, then using the diagonal could still be.
We've been using modal damping for the last 20 years, virtually in all analyses. And yes, it's slightly more expensive, but compared with anybody else's software, we're still a fraction of the time that they're requiring to do their analyses. That's with all the large frequency analysis to begin with, and the complications of the fully populated damping matrix during the time history.
Yeah, because you don't update it, right?
Well, it's not updating, and that is a totally. But for most, we don't have the data. You talk about the reduction in the stiffness. That's the localized deformation that you've reduced. The whole structure's stiffness hasn't changed by that much. The 1 degree of freedom structures, yes. Multi-degree of freedom frame, no. You don't see that great reduction in the total stiffness.
There were a couple of questions on the floor.
Yeah.
I want to keep people. You probably
thanks for the awesome presentation. My question is around implementation of Rayleigh damping that you've used in the examples. And if I'm correct, you've selected a couple of fundamental modes, maybe mode 1 and mode 3. When we're implementing it in practice, we tend to use a wider modal range, so 1.5 times the fundamental mode, and then
Okay.
90% of mass participation. I'm wondering if that, you know, and part of the reason for that is to try and overcome some of these issues. I'm wondering if you see that as being capable of mitigating some of the issues that you've raised here.
Well, it really, yeah, I think it really depends on the type of structure that you analyze. When you say,
Particularly
1.5,
for
yeah,
large degree of freedom,
yeah.
you know, several
But
dozen.
sometimes we could have nasty elements in the structures that have very huge frequencies in the structures. Then you could still end up with very high damping. There. So yeah.
I had that row with CSI at the 2017 conference in San Diego. The very high stiffness associated with their so-called rigid plastic joints does give enormous damping ratios to the high modes. And those high modes tend to be the rotational modes. And of course, they're the ones that excite as soon as you form a plastic hinge, because the beams will let go, the joints can now rotate. So you get a large rotation relative to the lateral displacements of the frame. And those rotational modes, I know it's been common practice for a long time to spread the frequencies which you pick, but that does mean you get maybe down to 2% damping in some of the modes in between.
Yeah.
And well, it's a discussion. One other point I would make is that experimental evidence, if you take free vibration tests after a shock loading on a structure, the damping actually isn't viscous. The decay is not a constant damping ratio. The damping ratio changes with amplitude.
Yeah.
So that's also a worry.
Yeah. So there's why in one sense that we are not really in model physics here.
No,
So
this is the problem. We don't know what the mechanism
yeah, we
is.
don't know what mechanism. That's why we are. Well, work on this. My intention is not to match physics. My intention is to calibrate against data. And then hopefully we can have some simple model that could give what you want. And it doesn't give you additional, like Rayleigh, give you more than what you want. I mean, not in terms of number, but a lot of other things that actually throw it at you.
So the idea would be to implement this model and then gather the data to
yeah. So when I work on this model, that's why I said in that question that I had in mind, it's like I want to come up with a model that give people flexibility to do whatever they want to do. Of course, it's not physics, but at least within the range of numbers that they feel comfortable. And then in one sense, they give them flexibility to allow them to make adjustment and without involving huge amount of time to update it. And so when I work on it, my idea at first is to address the concerns by Edo that was like 7 years ago and talk about base oscillation. So then I think about flipping it. Then later I think about how I can implement it. Because it has to be feasible computationally. We cannot sit here waiting for a year. So when I work on it, I realized I can actually make it fast, reasonably, definitely slower than Rayleigh. You cannot argue that Rayleigh is the fastest possible. You cannot beat that. However, we just need to give a bit more time and then end up with something that we can live with. I think that is considered a good model. It's not about right or wrong. It's just about the model can give you what you want. I think in the end, it's the engineer to decide what should be the number that I feel comfortable with.
And so just presumably the model gives you the capacity to study the physical mechanism of that damping and represent it in an analysis.
Yeah, it's like hopefully, like let's say the amplitude dependent damping that you see, right? Measured from data. Granted, it's probably don't trace it from point to point, but from peak to peak, you see that. And in that sense, hopefully we could reproduce that within reason. Yeah, that's my intention and my dream. Yes, thanks.
Thanks, Professor, for your great talk. My question is about.
There's an echo sound, it's very huge. Speak up.
Want to define the damping ratio between different modes, like the more bell-shaped we have, the more will be the accuracy. But what about the range outside of those defined frequencies, like the slope, when we are leading towards the infinity or towards zero. So does it make any difference when we are using it in practice?
Good question. So usually,
Maybe just very quickly summarize the question.
oh, okay. So let me summarize the question. The question is about, let's say, I have a uniform damping only within a certain frequency interval.
Yeah.
But outside that, they now decay to zero. And do they have any effects on the response?
Yeah.
My answer would be, they do have some effects on the response, but hopefully they are being treated as, they are dying down. So the damping effects definitely less. And another thing is, usually we are only interested in the response within a certain frequency range. So we have good control of the response within a certain frequency range. Outside that, hopefully, their effects are not significant. You can control it if you find that they are become significant, you can keep pushing the upper limit and keep pushing the lower limit. So that's my answer.
Thanks.
Thanks.
Rayleigh damping, if I'm not wrong, usually just has two model frequencies required to calibrate the model, right?
Mm.
For your model, let's say, how many parameters should be calibrated? Like, how difficult is it to use? How many inputs are needed, basically?
So the control is based on the data that you have. So if my data point is, let's say 5% damping at mode 1, let's say 0.5 hertz or 2 seconds. And I just need this data, and the rest parameters can be calculated based on some kind of optimization curve fitting to give you what you want. So I didn't show that. So I developed some kind of GUI that could give the uniform damping based on the range of the frequencies that you like. Let's say between 0.1 hertz to 10 hertz, which is a reasonable range. Then there's some formulas to tell you that what should be the numbers, parameter values to give you that. Or there's another GUI that could do optimization, do curve fitting for you. Yeah.
I have just 2 questions. You talked about tangent stiffness only, proportional damping. Showed some examples. Can you comment on initial stiffness only, proportional damping, so removing the mass term? And second question, what are your, I'd be interested to hear your thoughts on the recommendations in PEER, which is to combine majority of it being modal damping, combined with a small fraction of Rayleigh damping.
So the first question is about if I make it Rayleigh damping proportional initial stiffness.
Yeah, initial stiffness only, proportional damping, so without the mass term.
Oh, without a mass term.
Yeah.
Yeah, so definitely that will always give you positive damping, but you can only control the damping on mode 1. Beyond that, it's just follow the curve.
And it's linear with frequency.
Yeah. So in that sense, that means you actually reduce your flexibility. I mean, controlling the curve.
But I guess, is it a damping model that should be considered? Or
I would not recommend that.
The Japanese used to use that, but it was usually for 1 degree of freedom per story. So they didn't have a great frequency range in the structure. But for not general nonlinear time history, I think Raleigh's bad, but that's even worse.
okay.
Yeah.
And what about the combination of a majority of the damping being a modal damping? Combined with
Possible for formal 3D, isn't it?
Well, it's a PEER.
Yeah, I think it's because it's what's in perform 3D.
I thought you can also implement SAP and CSI.
There's also in a lot of books that actually
I know, but
more damping, and then that's why it's
I think it's because they don't want to compute all the frequencies.
yeah, that's for that reason.
It's going to give you this a sort of fully, no matter how many modes you take, you're going to end up with a fully populated damping matrix. So, okay, yes, the eigenvalue problem's a bit big if you want all the modes, but so far we haven't been bugged with that. We've managed to do that. It's an initial slight cost, but after that, who cares?
So what is the general recommendation then for users of damping models?
Well, it depends what your program's got.
Yeah.
Going to Jonathan's point, one option being to broaden that,
Yeah.
that range. And besides that, we've got limitations on what commercial software can provide us. So, users need.
In one sense, indeed,
solid
yeah, kind of.
guidance.
I kind of also this why I want to talk to Ethel about the Romoko. I also want to talk to because I have something using Abacus quite a lot, so I would want to talk to them and see whether it's possible to have this model implemented. And right now, definitely is in OpenSeas, available in OpenSeas, but only up to the global damping. Yeah, the elemental has been tried, and then the stick dependent one, because that then depends on how. So it's like when I give you a lot of flexibility, that means that you have to make a lot of decisions, and how the decision can be implemented, become like user interface experience type. So how can we handle that? I think it can be done. Definitely a lot of discussion between me and developer and the Abacus developer. Hopefully they, in one sense, I talked to an Abacus developer years ago. I said I work on some beam column elements. I said, we didn't try to implement it. The answer from them was, we don't care about what developer thinks. You only care about what users think. So that means in order for the model to be available, there has to be some feedback from the users. Users said, Rayleigh sucks. Sorry, bad mouth. So Rayleigh is not good enough. So can we have another model? Wilson model, okay, but I want to try something more than that. Can we have more? When they hear from you, then they would be happy for me to approach them. Until then, they don't care about me. They don't care about developer. They care only about users. Users say, Romoko can do this, so I'm not going to use Abacus. Then Abacus developer would come and say, I have it.
But users are driven by what's in the code, and the code is driven by what research.
Exactly.
I have a question about this. I see the new codes are asking us to use about 2% for time histories.
Yeah.
Why are they still playing with a 5% spectra? You know, scale your earthquakes to 5% spectra, then use a 2% damping. Totally unrealistic.
Yeah.
And the stag is we have a 2% spectrum, you're going to up it by about 50% on the current code. So not worried.
And I know the CSOC is trying to come up with some guidelines on the time history. Recently, they asked for feedback. And I approached them and I said, they said, Rayleigh damping with initial stiffness proportional would lead to spurious. So if that's concern, you use Rayleigh with tangent. So I said, no, even you use tangent proportional, it will still give you that, as I have demonstrated in my examples. Yeah, so I think we can do better than that. This is what I try to tell Tim and others. Yeah. Thanks.
Yeah, I think we're about 15 minutes past the sort of nominal end time. So I think there are obviously plenty of follow-up discussions on this. I guess if we haven't got, we've looked through the questions here and got to every one of them. I think there's others that probably still have further questions for Chinlong, but maybe I just suggest that you reach out to him.
Feel free to email me.
Continue that discussion. But otherwise, I'd like to thank everyone that attended online, as well as those that attended here in person, as well as, of course, Chinlong as our presenter this evening. So thank you very much.
Thank you all.